Have you ever stopped to listen? Just for a moment, in a quiet room, listen to your computer. You'll likely hear a gentle, persistent hum. It's the sound of a fan, tirelessly spinning away. This little device isn't just for show, it's a vital organ for the digital brain of your machine, the CPU. But why is it there? Why does a device that works with something as ethereal as information get so physically hot? The answer takes us on a journey deep into the nature of reality, connecting ones and zeros to the fundamental laws of physics, laws that govern the entire cosmos. It's a story about energy, order, and an unavoidable cosmic tax on thinking. That whirring sound is a battle against heat. Inside that tiny silicon chip smaller than your thumbnail, billions of microscopic switches flip at unimaginable speeds. Every click of your mouse, every letter you type, every frame of a video you watch translates into a frantic storm inside the CPU. This storm is a physical process. Electricity, a river of electrons, flows through infinitesimal channels, guided, stopped, redirected. Each operation generates a tiny puff of heat, a whisper of warmth. But billions per second become a roar of thermal energy. This heat isn't only sloppy engineering, it has a deeper cause. It ties to the second law of thermodynamics, the rule that shapes time and the fate of stars. In any closed system, disorder, entropy, tends to increase. Processing information, especially erasing it, is fundamentally linked to that rising disorder. So next time you feel that warmth, don't see just an inconvenience. Think of it as a physical manifestation of thought, the thermodynamic cost of computation. This essay explores that hidden heat. Could we ever build a computer that doesn't get hot? Feel the warmth? To understand the heat, we must first journey into the heart of the machine. Imagine your CPU not as a single object, but as a vast metropolis built on a sliver of silicon. This city is incredibly dense, populated by billions of inhabitants. These inhabitants are called transistors. A transistor is a microscopic switch. It can be on, allowing electricity to pass through, or off, blocking its path. These two states are the physical representation of binary digits, the ones and the zeros. They form the fundamental language of all computers, every calculation, every image, every sound. When your computer performs a calculation, say adding two numbers, it's a choreographed dance of electricity through this silicon city. Signals are pulses of voltage traveling along tiny copper pathways, arriving at clusters of transistors called logic gates. Logic gates are the basic building blocks of computation. An AND gate, example, inputs 0, 0, 0, 1, 10, 11, only outputs 1 when both inputs are 1. By combining billions of these gates, engineers build circuits that do amazing tasks, from simple arithmetic to rendering entire virtual worlds. Now let's follow the energy. To make transistors switch, to push electrons through gates, we must apply electrical energy. Electrons don't flow effortlessly, even the best conductors have resistance. Collisions transfer energy to atoms. Vibration is heat. This is Joule heating, like a bulb filament or a toaster. Engineers reduce resistance and improve efficiency, but some heat is unavoidable. Pushing current always wastes some energy as heat, but that's only part of the story. For a long time, physicists thought computation could, in principle, be performed with zero energy cost. However, in 1961, Rolf Landauer at IBM uncovered a profound connection between information and thermodynamics, Landauer's principle, changing our understanding forever. He realized the crucial energy-costly step isn't processing information, but destroying it. The act of forgetting is what generates heat. Any logically irreversible manipulation such as erasing a bit must increase the entropy of the environment. To erase one bit, resetting to a known default, you must dissipate a minimum amount of energy as heat. This is a fundamental physical limit. It's a cosmic tax on tidying up information. The universe demands heat for every bit you throw away. Consider an AND gate. If the output is 0, you can't infer the exact inputs, 0, 0, 0, 1, or 10. Information has been lost. You can't run it backward. Landauer quantified the minimum energy. E equals kTln2, minuscule at room temperature yet paid astronomically often inside modern CPUs. Billions of resets per second, converging inputs, discarded information. Each erasure pays its tiny tax. Together they form an inescapable portion of CPU heat. To truly grasp this, we need to talk about entropy. Entropy is often described as disorder. More accurately, it's a measure of uncertainty. The number of microscopic arrangements that look the same macroscopically. Air in your room, countless arrangements, high entropy. All molecules crammed in a corner, highly specific, low entropy. The second law, total entropy of an isolated system never decreases. Things tend to move from order to disorder, from low to high probability. An ice cube, ordered water molecules in a warm drink, disordered molecules, will melt, spreading order and increasing total entropy. The universe is on a one-way journey toward maximum entropy, the heat death. In the 1940s, Claude Shannon quantified information as surprise. His formula mirrors thermodynamic entropy, not a coincidence. Information is, in a real sense, the opposite of entropy, a measure of order and certainty. When a computer holds a bit, 1 or 0, it is low entropy, we know its state. It's ordered. Erasing a bit lowers order inside memory. The second law demands the outside world's entropy rise at least as much by releasing heat. Let's make this concrete. Imagine one bit is a single gas molecule in a box divided by a partition, left is 0, right is 1. Because we know which side the entropy is low. To erase, we force a standard state, 0. First, remove the partition. The molecule can be anywhere, information lost, entropy increases. Then compress from the right with a piston pushing the molecule left. Collisions transfer energy, the molecule and walls heat, that heat dissipates into the environment. We erased the bit, but we had to do work and generate heat. Order inside is paid for by more disorder outside. An irreversible gate is like removing the partition. Resetting transistors is like pushing the piston. Reset requires energy and must dissipate a minimum amount as heat, the Landauer bound. This is not resistive heat. It's the fundamental heat of forgetting. It's the physical price of logical irreversibility. Could we avoid paying this price? If irreversible operations are the fundamental source of heat, could we build a logically reversible computer? A computer that never forgets? Every operation would be perfectly invertible. From outputs you could recover inputs, no information lost, no standard and/or, those are lossy. Use Toffoli or Fredkin gates, keeping outputs equal to inputs. Two outputs copy inputs to preserve info. A third performs the operation but remains invertible, like leaving breadcrumbs. In principle, flipping bits could dissipate 0 energy. Move the partition very slowly, adiabatic. Run computation in reverse, return to initial state, reclaim energy. But to get an answer, you must read the result, then erase intermediate data. That erasure is irreversible. You still pay the Landauer tax at the end when you throw away the scaffolding. The dream? Make the computation heatless, even if cleanup costs energy. A fully reversible computer is elegant, but the device you are using is profoundly irreversible. Modern CPUs are built on irreversible logic, from smartphones to supercomputers. Why? Immense practical challenges, trade-offs between theoretical perfection and performance. Reversible logic is complex. An AND is a handful of transistors. A reversible Toffoli is significantly more. Processors would be larger, more complex, and slower. Modern computing is a race for speed. Operations per second. Easier to build faster, hotter chips, then invent better cooling. Reversible machines must preserve all intermediate information. Imagine a weather forecast storing every step. Only at the end can this history be uncomputed to recover energy, with staggering memory management overhead. Our CPUs are hot not just because of Landauer. They're engineered for speed, shouting their calculations rather than whispering adiabatically, mixing Landauer's tiny tax with much larger joule heating and brute force inefficiency. We choose to pay this thermal price. Now we can return to that gentle whirring sound, the spinning fan, with new appreciation. The fan, heat sinks, and heat pipes form the respiratory system of your computer, performing exhalation. All the heat, frictional resistance, and the fundamental heat from erasure is generated in a tiny chip. If not removed, consequences are catastrophic. A heatsink, aluminum or copper, with many fins, sits on the CPU, drawing heat and spreading it across a large surface. The fan blows cooler ambient air across fins, accelerating convection. Hot air is expelled from the chassis. This cycle, conduction to the sink, convection to air, keeps the CPU in a safe temperature range. Without active cooling, a high-performance CPU overheats in seconds. Past 100 degrees Celsius, structures fail, electrons flow chaotically, errors multiply, crashes ensue, damage becomes permanent. Thermal sensors throttle or shut down systems to prevent this. The faster we want computers to think, the more irreversible operations per second, the more electrical power we pump in, the more heat we must remove, from simple fans to liquid loops to data center HVAC. Vast energy just to handle the thermal consequences of thinking. Will computers always be hot? Are we bound to the cycle, computation, heat generation, frantic cooling? For now, likely yes. The paradigm is fundamentally irreversible. But researchers keep pushing. The dream of a cool, efficient computer is waiting for a breakthrough. Quantum computing, qubits in superposition, evolution via the Schrödinger equation is inherently reversible. In principle, no erasure, no Landauer heat. Yet current quantum machines require extreme cooling to stay coherent. Beyond quantum, ballistic computing, electrons in vacuum, adiabatic computing, reversible logic runs slowly to minimize loss. Today, September 29, 2025, we live with hot, fast, wonderfully powerful, irreversible machines. The warmth from your computer reminds us of the thermodynamic price of every calculation. Science turns curiosities into tech. Principles from Landauer, Shannon, and others explain why computers get hot and sketch a blueprint for a cooler future. The silent, cool computer remains a distant dream, grounded in the laws of our universe.